Hi everyone. So as I mentioned a couple of times already, my talk is not about biobanks, but it's about some cool old statistical methodologies and how they apply to new or semi-new problems, and the connection to biobanks. We can talk about that. I think those very interesting connections that we can think about. Okay, so let's see. Okay, so I'm going to be talking about using MCMC and importance sampling for tail calculations and using expectation maximization for pet reconstruction. So since I'm not allowed that much time, let's just dive into the first sort of motivating application that we're going to be talking about, which is about doing permutation testing and in particular multiple testing in the context of permutation testing. So I'm going to introduce all these sort of traditional things like permutation testing when we talk about MCMC, when we talk about EM. Feel free to stop me if I'm going too fast. So it will just be like quick reminders. So what's a permutation test is we have some test statistics that we measure on our data, and we want to find the probability that a properly defined random permutation, where how to properly define random permutation basically depends on the distributions the data come from and the null distribution we have in mind. So a properly defined random permutation of the data gives a higher value for the statistic than we see in our actual data. So that's a very general notion of a permutation test. So permutation tests are ubiquitous all around us. And for example, if we think about Fisher's exact test for 2x2 tables, which I hope everyone's heard of, that's really a permutation test, except that it's maybe not the way we're used to thinking about permutation tests, because we have an analytic way of counting how many permutations give higher statistic than our original data, so we don't actually have to perform the permutations. But that really doesn't matter conceptually. It's conceptually a permutation test. So here we can count. We don't need to sample. Of course, if we have big in this running example, if we have tables that are bigger than 2x2 and we want to do something like Fisher's exact test, then we would just sample permutations. And if we do enough permutations, we would get a good approximation of the same thing we can calculate exactly for a 2x2 table. So, so the analogy would be a permutation test is like a generalization, or Fisher's exact test is just an example of permutation test. And also doing random permutations is an example of a permutation. So one thing we have to worry about is how small are the p-values we can estimate with the permutation test. If we can do the calculation analytically like 2x2, we don't have to worry because we get an exact p-value. But if we have to sample, then we have to worry about the fact that we know that in many scientific areas, and probably the best known example here is GWAS, but also in particle physics and other areas, it's become well understood that we need really small values, small p-values to confirm findings, essentially because of multiplicity. Explicit or implicit. In particle physics, it's usually implicit multiplicity. But the 5 sigma rule in particle physics is very much like the 5 times 10 to the minus 8 threshold in GWAS. Okay, so we have we have to confirm really small p-values. And why is that a problem with permutation tests? Let's assume that the true permutation p-value denoted by Q, so that's the true probability over permutation space that the permutation test statistics is bigger than the observed test statistic. So if we randomly sample m permutations, it's easy to see by simple binomial calculation that the permutation test p-value has standard deviation, which is like the square root of Q over m. Why is that a problem? So that basically means that if I want to get an accurate estimate of Q, I basically need something like 10 over Q or maybe 100 over Q, depending how accurate I want my estimate to be. That's the number of permutations I need to estimate to basically get a standard deviation that's on the order of, if I want a standard deviation that's on the order of 1% of Q, then I need actually 10% of Q, then I need 100 over Q permutations. So when I need Q to be order of 10 to the minus 8, that becomes a big problem, right? Because that means that if I'm interested in p-values of this magnitude as I am in GWAS, then I need on the order of magnitude of, what, 10 to the 10 permutations, 10 to the 9 or 10 to the 10 permutations. So that means that at this point, it seems like permutation tests are not practical for getting very small p-values. Okay, let's step back and think about this problem in a slightly more general setting, and this idea of estimation or estimating expectations by random sampling. So the general setting we think about, we have some distribution over some space. So the space is X and is this calligraphic X, and the distribution is F. And I want to estimate the expectation of some function. So I'm interested in this integral, but the two functions have different meaning. This is the density function or probability function. That integral can be a sum as well. And this is the function I want to calculate its mean. Okay, they have two different roles. It translates into this integral, but conceptually, one is the distribution and one is the function. So that means now if I have some way of sampling directly from F, then what do I do? What can I do to estimate this integral or this mean? I can get a bunch of samples from F, right? So I can sample from F. So I get a bunch of IID samples sampled according to distribution F, and then I average H over the samples I got. So this is calculating the average of H over the M samples I got, over the big M samples I got from the distribution. And this is actually exactly what we do when we do a permutation test, right? When we estimate a permutation p-value based on sampling. So when we do a permutation testing, this calligraphic X is the space of all possible permutations. F is just uniform, so because I give all permutations equal probability, all permutations are equally likely. And H is very simple, just an indicator function, right, of whether the test statistic is bigger than my threshold or smaller than my threshold. So this general algorithm is also embodied in doing in estimating permutation p-values from sampling. Okay, so and now we can think about our problem and the problem is that if my sample is not very big, depending on the setting of the problem, if my sample big M is not very big, then the variance of my estimate might be too big for me, right? The variance of my estimate based on sampling. And in the instance of permutation testing, this is exactly the problem we had, that the variance was too big for us unless the number of permutations was overwhelmingly big. So we need to find a way to deal with this big variance of the sampling-based estimate. In this case of permutation tests or of permutation p-values, but it's a general problem. And so the main idea behind this notion of importance sampling, which is a very important notion that's maybe understudied in education programs I know, is that instead of sampling from F, let's consider sampling from a different distribution G. Okay? So, and why would that be a good idea? Because, first of all, what would we do if we sample from G instead of from F? We are still interested in the expected value relative to F. Our problem is the same problem, but now we're sampling from a different distribution. So now in our estimate, it's easy to prove that what we have to do is we have to weight by this ratio of the distribution we want to the distribution we actually sampled from. Okay, so we can estimate based on sampling from a different distribution G. It's still going to be an unbiased estimate of this value mu we are interested in, But it turns out that this can have much smaller variance. And generally, what we want to do to get small variance is we want G to look not like F, but like the product of H and F. And basically, we can show that if we can get G to be exactly the product of H and F, then actually that would be the most efficient thing we can do, and basically it would give variance 0. But let's not worry about having variance 0. In general, we can convince ourselves, and I'm not going to show it here, that it's a good idea to try to make G as similar as possible to the product of H and F. And then we're going to get a low variance for our estimate. Okay? So for permutation testing, what it means is that G has to look as similar as possible to that indicator function, right? Because F is actually constant. It's like a very simple instance of this mean estimation problem of this. F is constant and H is just this indicator function. So basically, we want an important sampling function that looks like the indicator function. So basically, that's what we sort of aspire for. So that leads us to looking for an importance distribution that looks just like a step function, but maybe for reasons that I'm just going to hint at, we can't really deal with step functions. So maybe we want some continuous functions that look similar to the step function as the importance distribution to sample from. Okay, so let's say that we choose one of these functions. Now we want to do importance sampling on permutation space using this importance function. That's really not a trivial problem because I don't really know how to sample a random permutation according to something that's basically an arbitrary distribution over permutation space. I know how to sample a permutation and look at its G value, but I don't know how to sample according to G. So that means sample with higher probability permutations that are above the threshold than permutations that are below the threshold. So I need to, if I want to try to implement this, I need to solve the sampling problem. And what I'm going to do for sampling is use Markov Chain Monte Carlo, MCMC. And the general idea of MCMC is I have some weight function, as I do here, G, and I don't know how to sample from G. But it turns out that I can easily build a Markov chain whose stationary distribution is proportional to G. And why is that useful? Because if I take a Markov chain whose stationary distribution is G, then I can just run this Markov chain for a while, and then I automatically get a sample from G. Okay, so that's actually a way to sample, and I gave a tutorial on MCMC a couple of years ago here. So I'm not going to get into more details, but this is directly applicable to our problem. We can sample permutations according to the importance function that we want. And here there's lots of fine points on how to actually design effective MCMC algorithms, and that's related to the fact that I can't really implement an MCMC algorithm for a step function. I need these continuous functions so I can do a Markov chain, and I can run the Markov chain efficiently. So we're not going to get into the considerations, but there's various considerations, and some theoretical ones, and some you just have to empirically try different things and see what works. So, but conceptually, we want importance functions that prefer things above the threshold, and we want to choose ones for which MCMC works well. And when we put all of this together, we actually have an algorithm, right? So an algorithm we call MCMC-IS for MCMC importance sampling. This is the master's thesis of Shuli Halperin, my student. So basically, we want to choose a weight function that is similar to the step function, but also amenable to MCMC. We use MCMC, and that way we get importance sampling samples from G. And basically, now we can use this weighted formula that we showed to estimate the permutation p-value. And really, because we don't really know how what good G looks like, considering both the important sampling aspect and the MCMC aspect, then really this should all be wrapped in function that tunes G using different considerations to get a good, efficient MCMC algorithm, and also low variance for the estimates. And I won't go into details here because of my time limitations, but that's actually included to some extent in the algorithm we have already. What I wanted to show you is that this actually works surprisingly well. And what we have here on both sides, we look at the left first, is running MCMCIS for only 1 million permutations. Okay, so, and that includes the burn-in, for those who know what that is for MCMC. That's actually doing a total of 1 million permutations. And we saw already that there's no way to estimate the p-value well on the order of 10 to the minus 8 using 1 million permutations. I need 10 to the 10 permutations to do that. And this is actually estimating p-values of 4 times 10 to the minus 7 and 7 times something like 10 to the minus 8 total, estimating them with 1 million permutations. We should look at the blue and green bars. The orange, I haven't told you anything about. It's some competitor that we don't care about right now. But if we look here, we see in green is basically the naive permutation estimate. We know that there's no way of estimating this p-value with 1 million naive permutations. And we see that it's this is on the log scale. So this basically means that we get nothing out of doing 1 million permutations for a p-value of 10 to the minus 8. But we see that we get very accurate estimates using 1 million permutations with the important sampling implemented with MCMC. And the one on the right is really interesting. It's just the start of something, but this is taking chi-square p-values for 3x2 tables, so tables where we don't have a Fisher exact test, and comparing the chi-square p-value to the MCMCIS estimates with 1 million. So a p-value of order 10 to the minus 11, we don't get perfect estimates with MCMCIS. This is just a histogram of multiple runs of the MCMC importance sampling. And the thing I wanted to emphasize here is, first of all, that the range here is just like between 1 and 2 times 10 to the minus 11. So it's actually within 100% error, or within one-fold error. It's actually pretty good that we can estimate this p-value with 1 million permutations. But once we believe that MCMCIS gives unbiased estimates as it should, the interesting thing is that this histogram is not centered on the chi-square p-value. And in all cases, the histograms are actually centered on lower values than the chi-square estimates. And that's nice if it's a general phenomenon which is to be determined, because if the chi-square p-values are conservative, we should all care about it, right? Because then getting a less conservative, more accurate calculation would give us more discoveries, more papers, more Nobel Prizes, and that's what we care about, right? So that's a motivation why being more, getting the exact permutation p-value can actually be beneficial.
I can see how this would be a selling point. Lower your p-values, use our algorithm. But if they're consistently lower, then couldn't you just correct your p-value?
Yeah, sure. If you figure out.
It's all wrong by a certain estimate.
That's perfect. I don't know that there's theory on the. I don't know that there's theory on the consistent error of chi-squared as an estimate of the permutation p-value. I think it's true, but also some people disagree even with the definition that chi-square is an approximation of the permutation p-value. But I also don't know. These are just a few examples. It might be. We know that the chi-square is just an approximation, right? So doing the exact p-value by getting really good MCMCIS algorithms that can estimate this with a very accurately with a realistic number of permutations, I think it's going to be a better thing anyway. If it's true that it's consistently that it's consistently over-pessimistic, the chi-square p-value, then it's possible to derive some consistent correction based on theory or based on wide empirical work. I mean, that's to be determined.
I have one more question about the application of this. You know, there are a lot of times where I've encountered people making plausible arguments that, let's say, the correction on bond-forming correction for GWAS,
Yeah.
more or less bond-forming correction,
Yeah.
is too strict.
Yeah.
But also, just in my experience with data sets, it's pretty good because things that are less than 5 times 10 to the negative 8, they just don't replicate as well. And
Okay.
so, you know, in terms of the application, you could say, well, you know, we're throwing away a lot of real things, and you're probably right. Like that strata of like 5 times 10
Yeah.
to the negative fifth into the negative 8 is there's going to be more true things in there than not, but it still functionally works quite well. So I'm not sure. This is more general than just the GWAS
Yeah.
space, but do you have any thoughts about, you know, downstream how useful this method is in terms of being able to find reproducible results, which is really
Right.
one of the main reasons
So
we generate these p-values?
there's a lot to unpack in your question. One thing to unpack is publication bias, right?
Right.
So the fact that that you do a Bonferroni correction, but in fact there's a lot of other studies going in the background, means that even though your Bonferroni correction is over-conservative, considering all the other studies going on in the background, it might not be conservative. So, and that's extremely difficult to, that's like a big minefield to start walking down. The other thing is when you do permutation-based correction instead of Bonferroni, you actually don't have to worry about estimating tiny p-values, right? Because you would just do, you would just take the minimum or the, whatever, the maximum test statistic and look for the empirical distribution of the permutation distribution of the maximum test statistic, and that actually, then you would correct at the 5% level, not at the 5 times 10. So the number of permutations you have to do is not that big. You have to do a lot of work for each permutation because you have to run your entire GWAS for each permutation. So that's a slightly different setting. That would be, that would be a situation where you just worry about calculating tiny p-values, not about whether Bonferroni is the correct correction or not. So how am I doing on time? 5 minutes?
5 minutes.
Okay, so I'll just go very quickly over the second one.
So I'm just wondering, how does this, how much of this is parallelizable?
Sorry, what?
Is parallelizable. Can be run in parallel. So one of the nice things about importance sampling is, of course, you can draw these samples in parallel, and ultimately you aggregate all these.
Sure.
But the MCMC now introduces.
Right.
So I'm just trying to think of this in the context of large data sets, and if you were to try to implement this on large data sets, the compute becomes a limiting factor.
Right.
So is there a way to combine it and make it parallel?
Very good question. I think there is, and the reason I say I think there is that this is actually not as sensitive to the importance distribution as you might think, to the importance sampling distribution, and then you can use each importance sampled permutation you can actually use for all your statistics. You don't have to calculate just one statistic from it. The other thing is you can run multiple chains in parallel. There's some overhead because you have to do burn-in for each one of them, but then you can get many samples in parallel. So there's a lot to think about in this, but it's somewhat parallelizable, I think. Okay, so I'll just give headlines on my second talk. That's a big, my second half, that's a big challenge to try to just give main ideas. What I'll do is I'll introduce the problem and the sort of traditional algorithm, and I won't go into what we did, just to say something, tell a story that I think is interesting. So this second motivating application is PET imaging, and in PET, what I have is I have a bunch of pixels or voxels, and I have my sensors in a circle or in a ball around the voxels. So that's the setup. And what happens is that every time there's an event, and we'll say what an event is in a moment, in a voxel, then actually it shoots two particles in opposite directions in 180 degrees, but it doesn't have to be in the middle. The voxel can be here. And then two sensors sense the event. And when two sensors sense at the same time, that means that there was an event, there was an incident somewhere on this line. We don't know where it is. But when there's an event somewhere on this line and it shoots in that angle, then we sense here and here. Okay, so that's the setup. And the point is that this actually gives us a Poisson regression problem. Because what we observe are these simultaneous events in two sensors. Every time we send something simultaneously in two sensors, that's an event. Otherwise, we don't note an event. And it's easy to show that these counts are actually Poisson distributed with parameters that depend on what we care about, which is the image, the sugar concentrations in the voxels. Each voxel has some sugar concentration, and that determines how many events happen in this voxel. So lambda are the parameters we want to estimate. A is complicated, but we can assume known transformation matrix, and then we measure what we see is this. What we see are these incidents, and therefore it's just a Poisson regression problem. But it's a Poisson regression with an identity link function and not the standard log link function. And the interesting thing is that things hopefully many of us learned in statistics class cannot be used here, because there's too many parameters and way too many observations to do things like to do basically second order methods. And the cool thing I wanted to get to, so I'll skip the very important refresher on EM, and I'll just tell you the nice thing for statisticians is that a couple of statisticians 40 years ago invented a really cool method for fitting this that's based on basically applying EM to this problem. And the EM updates give a very intuitive formula when we look at them. So this is the total EM update after the E and the M step. And 40 years later, it's still what people are using with slight modifications, but basically it's still what people are using. And I don't have time to get into it, but what we did is say that this model, this Poisson regression model actually isn't perfect because of various things that happen in life, like this particle shoots but gets blocked, so I don't observe the two sides, I don't know that something happened. Or the particle gets deflected, and so I observe something that's not actually, the event is actually not on the line of sight of the two sensors. Or the really cool thing is that two events happen simultaneously, both get blocked or almost simultaneously, and then I see something that's the result of actually two halves. And what we did is a correction to this phenomenon, which is actually very common. And I'll skip over what we did and just show you this image. This is a famous sort of simulated PET data set. This is the true image. This is what the regular EM gives, and this is what our modified EM gives, which takes into account these randoms, which are not really true incidents. Okay, so that's enough. Thank you. And of course, I'm happy to talk offline to anyone interested in that PET or in EM in general.